Part 3. The mathematics of quantum physics. Quantum physics relies on sophisticated mathematics to describe the behavior of particles and systems at the smallest scales of reality. At the heart of this mathematical framework is something called the wave function, which is a mathematical way to describe where a particle might be and what it might be doing. This concept represents one of the most profound departures from our everyday understanding of how objects behave in the world around us. The wave function doesn't tell us exactly where a particle is, but rather gives us the probability of finding it in different locations. It's like having a map that shows you where you're most likely to find something, rather than its exact location. This probabilistic description extends beyond just position. The wave function encodes information about all possible properties of a quantum system, including momentum, energy, and spin. When we square the wave function at any point in space, we get what physicists call the probability density, which tells us how likely we are to detect the particle in that region during a measurement. The Schrödinger equation is the mathematical tool that tells us how the wave function changes over time. This equation is to quantum physics what Newton's laws are to classical physics. It's the fundamental rule that governs how quantum systems evolve and behave. Developed by Austrian physicist Erwin Schrödinger in 1925. This partial differential equation describes how the quantum state of a physical system changes with time. The equation takes different forms depending on the system being studied, but its core principle remains the same. It determines the time evolution of the wave function based on the energy properties of the system. What makes the Schrödinger equation particularly elegant is its deterministic nature. When it comes to the wave function itself, while individual measurements yield probabilistic outcomes, the wave function evolves in a completely predictable way according to the equation. This creates a fascinating duality. The mathematical description is deterministic, but the physical reality it describes is fundamentally probabilistic. Unlike classical physics, which can give exact predictions, quantum physics deals in probabilities. We can calculate the chance of finding a particle in a certain place or state, but we can never be completely certain about the outcome of any single measurement. This probabilistic nature is fundamental to quantum physics, and isn't just due to incomplete knowledge, it's how nature actually works. This principle, known as quantum indeterminacy, was initially troubling too many physicists, including Albert Einstein, who famously objected that God does not play dice with the universe. The mathematical formalism extends far beyond just the wave function and Schrödinger equation. Quantum mechanics employs complex numbers, linear algebra, and operator theory to describe quantum states and their transformations. Observable quantities like position, momentum, and energy are represented by mathematical operators that act on the wave function. The relationship between these operators reflects deep physical principles, such as Heisenberg's uncertainty principle, which states that certain pairs of properties cannot be simultaneously measured with perfect precision. Matrix mechanics, developed by Werner Heisenberg, provides an alternative but equivalent mathematical formulation to Schrödinger's wave mechanics. In this approach, quantum states are represented as vectors in an abstract mathematical space called Hilbert space, and physical operations are represented as matrices. This formulation proves particularly useful for systems with discrete energy levels, such as atoms and molecules. The mathematical framework also incorporates the concept of superposition, where a quantum system can exist in multiple states simultaneously, until a measurement forces it to collapse into a single definite state. This phenomenon has no classical analog and requires careful mathematical treatment using linear combinations of basis states. Understanding these mathematical foundations is crucial because they reveal the true nature of quantum reality. Unlike classical physics, where mathematics simply describes what we observe, quantum mathematics appears to reveal the fundamental structure of reality itself. The equations don't just predict experimental outcomes. They suggest that the universe operates according to principles that challenge our most basic intuitions about the nature of existence, causality, and the relationship between observation and reality. Part 4. Simple examples to explain quantum physics. Example 1. The double-slit experiment. Let's walk through the famous double-slit experiment step by step. When you shine a light through to tiny holes in a barrier, something remarkable happens on the screen behind it. Instead of seeing two bright spots where the light passes through the holes, you see a pattern of alternating bright and dark stripes. This pattern proves that light behaves like a wave, because waves from the two slits interfere with each other, creating regions where they add up to make bright spots and regions where they cancel out to make dark spots. But if you look at the light very closely with sensitive equipment, you discover something amazing. The light actually arrives at the screen as individual photons, tiny particles of light hitting the screen one by one like raindrops. Even when you send photons through one at a time, the stripe pattern still appears. This means each individual photon somehow goes through both slits simultaneously and interferes with itself, creating the wave pattern we observe. The truly mind-bending part comes when scientists try to determine which slit each photon actually passes through. When they place detectors at the slits to watch the photons, the wave pattern completely disappears, and instead you see exactly what classical physics would predict: two bright spots directly behind each slit. The very act of observation changes the behavior of the particles from wave-like to particle-like. This demonstrates the fundamental quantum principle that measurement affects reality. At the smallest scales, this experiment has been repeated with many different particles, from electrons to entire molecules, and the results are always the same. The quantum world operates according to principles that seem to violate our common sense. Yet these principles are fundamental to how the universe works at its most basic level. Example 2. Atomic energy levels. Electrons in atoms provide another clear example of quantum behavior. These electrons can only exist at certain specific energy levels. Like people standing on the floors of a building, they can be on the first floor, second floor, or third floor, but never between floors. This quantization of energy is what gives quantum physics its name, from the Latin word quantum, meaning how much. When an electron jumps from a higher energy level down to a lower one, it releases energy in the form of light. The color of this light depends on exactly how big the energy jump is. This is why different elements produce different colors when heated. Each element has its own unique set of energy levels, so each produces its own characteristic colors. This quantum behavior explains why neon signs glow in different colors. The electric current in the sign gives energy to the gas atoms, pushing electrons up to higher energy levels. When these electrons fall back down, they emit light of specific colors determined by the quantum energy levels of that particular gas. Neon gas produces the familiar orange-red glow, while other gases like argon create blue light, and mercury vapor produces blue-green light. The precision of these energy levels is so exact that scientists can identify elements in distant stars by analyzing the specific wavelengths of light they emit. Each element has its own unique fingerprint of spectral lines, allowing astronomers to determine the composition of celestial objects millions of light years away. This technique, called spectroscopy, has revealed that the same elements found on Earth exist throughout the universe. Moreover, these quantum energy levels explain why atoms are stable. In classical physics, orbiting electrons should gradually lose energy and spiral into the nucleus, causing all atoms to collapse. But quantum mechanics shows that electrons can only occupy specific energy states, and the lowest energy state, the ground state, is perfectly stable. This quantum stability is what allows complex chemistry and ultimately life itself to exist. Example 3. Quantum tunneling. Quantum tunneling demonstrates another bizarre aspect of quantum physics. In our everyday world, if you roll a ball toward a hill, the ball needs enough energy to get over the hill. If it doesn't have enough energy, it will roll back down. The barrier is absolute. Without sufficient energy, there's no way through. But in the quantum world, particles can tunnel through barriers, even when they don't have enough energy to go over them. It's as if the particle disappears on one side of the barrier and reappears on the other side, like a ghost walking through a wall. The probability of tunneling depends on factors like the thickness and height of the barrier and the mass of the particle. This impossible-sounding phenomenon is actually used in many modern devices. Tunnel diodes rely on quantum tunneling to work, and scanning tunneling microscopes use this effect to create images of individual atoms. Without quantum tunneling, many of our modern electronic devices simply wouldn't function. Flash memory drives, which store data in your smartphone and computer, use quantum tunneling to trap and release electrons in tiny storage cells. Perhaps most remarkably, quantum tunneling plays a crucial role in the nuclear fusion reactions that power the Sun. The protons in the Sun's core don't actually have enough energy to overcome the strong electrical repulsion between them and fuse together through classical means. Instead, they tunnel through the energy barrier, allowing fusion to occur at much lower temperatures than would otherwise be possible. Without quantum tunneling, stars like our Sun couldn't shine, and life on Earth would never have developed. Quantum tunneling also occurs in biological systems. Some enzymes use quantum tunneling to speed up chemical reactions, and recent research suggests that quantum effects might play a role in photosynthesis, where plants convert light into chemical energy with remarkable efficiency. These discoveries are opening up the new field of quantum biology, showing that quantum mechanics isn't just relevant in physics laboratories, but may be an essential part of life itself. Thank you for watching this part 3 and part 4 explanation of quantum physics. If this video is knowledgeable and interesting, give us a comment and like. Also share with other like minds too. If you haven't watched the video of part 1 and part 2, the video link is given below in description. Do not forget to subscribe my channel. Next video, part 5, quantum physics in everyday life, and part 6, the weirdness of quantum physics.